Okay, in our last class, we were discussing voltage regulation of a transformer. First of all, we have defined voltage regulation, then we have discussed about the mathematical formula to calculate voltage regulation, and then we have derived one uh, mathematical expression by which we can determine the voltage regulation from the machine parameters, that is per unit resistance and reactance when the load power factor is given. Okay, then we have determined the condition for zero voltage regulation. Now today we will discuss the condition for maximum voltage regulation. Okay, so here the voltage regulation expression for uh, lagging power factor load is given by this expression: voltage regulation equals to per unit resistance into load power factor plus per unit reactance into sine of load power factor angle. Okay, so now if we take the derivative of this expression with respect to theta 2, that means when the load power factor angle is varied or the load power factor is varied, then what happens to the voltage regulation, that we have to see. Okay, so taking derivative of this expression with respect to theta 2, we get this minus epsilon r sin theta 2 plus epsilon x cos theta 2 and equating it to 0 to find the condition for maximum voltage regulation. Okay, so the condition is tan theta 2 is equal to xe2 by re2, that means the ratio of reactance to resistance per unit reactance to resistance, and since the base impedance is same for both, while calculating both this per unit reactance and resistance, so we can directly write the ratio of reactance to resistance, equivalent reactance to resistance will be equal to the equal to tan theta 2. Okay, that is tangent of the load power factor angle. So this is the condition for maximum voltage regulation, and at that condition the power factor will be Re2 by Ze2. Okay, so when the power factor is equal to Re2 by Ze2, then the voltage regulation will be maximum, and the magnitude of that voltage regulation, that means the maximum voltage regulation, will be given by, if we put the value of x cos theta 2 and sin theta 2 from the expression of tan theta 2 and putting that value to the expression of voltage regulation, we will get this, that is epsilon r Re2 by Ze2, this is the value of cos theta 2, and epsilon x xe2 by Ze2, that this is the value of sin theta 2, and putting the value of epsilon r epsilon x in terms of this rated current and the rated secondary voltage, we will get this as the Ze2 per unit. That means the maximum voltage regulation will be equal to the per unit impedance of the transformer. Here Re2 square plus Xe2 square is Ze2 square, so one Ze2 will get cancelled out, and E2 by I2, that is the base impedance, so this becomes the per unit impedance of the transformer. So maximum voltage regulation is equal to the per unit impedance of the voltage regulation. So that is one more advantage of using per unit quantities. So if we know the per unit impedance of the transformer, then we can easily say that its maximum voltage regulation will be same as that of the per unit voltage regulation in per unit, and if we multiply it by 100, then we will get percentage voltage regulation. Is it clear?
Yes, sir.
Any question?
Yes, sir.
Any question? No. Okay, let us solve this example. So here one transformer, single phase transformer is given with rating 20 kVA and voltage rating 2500 by 500 volt. So high voltage side voltage rating is 2500 volt, low voltage side voltage rating is 500 volt, and the parameters are given. High voltage winding parameters are R1 8 ohm, X1 17 ohm, low voltage winding resistance R2 equals to 0.3 ohm, X2 equals to 0.7 ohm. Okay. So question is, find the voltage regulation and the secondary terminal voltage at full load for a power factor of 0.8 lagging and 0.8 leading. The primary voltage is held constant at 2500 volt. So here the high voltage side is used as the primary side. So that is why this high voltage winding parameters are denoted by R1. That means subscript 1 is used for high voltage side winding, and low voltage side winding subscript 2 is used. Okay. Load power factor is given 0.8 lagging one and 0.8 leading the second one. So first of all, how to calculate the voltage regulation? So here we have to refer all the quantities to the secondary side, that is the low voltage side for this case. So RE2, that is the total equivalent resistance referred to secondary side or low voltage side. So RE2 equals to R2 plus R1 into N2 by N1 whole square. So calculate this. R2 equals to 0.3 plus 8 into 500 by 2500 square.
So 0.62.
0.62. Similarly, calculate equivalent reactance using similar formula. XE2 is equal to X2 plus X1.
1.38.
1.38 ohm. Okay. 1.38 ohm. Okay. Now full load secondary current. Here secondary voltage is 500 volt and the transformer power rating is 20 kVA. So using these two data we can calculate the full load secondary current, that is the rated current. So that is I2 equals to 20,000, that is 20 into 10 to the power 3. Full load voltage drop in the secondary terminal voltage for a lagging PF is equal to E2 minus V2, that is the secondary terminal voltage drop. Okay. So that is I2 RE2 cos theta 2 plus I2 XE2 sin theta 2. So cos theta 2 is given, from that calculate sin theta 2. I2 we have calculated 40 ampere, RE2 we have calculated, XE2 we have calculated. So calculate sin theta 2 and put all the values. So sin theta 2 is equal to 0.6. So put all the values and calculate.
So 52.96.
52.96 volts. So that is the voltage drop. Okay. Now secondary terminal voltage. What is the secondary terminal voltage here? This V2. E2 is given 500 volt. So calculate V2. You know the difference, E2 minus V2. So E2 is given. So calculate V2.
447.04.
So 447.04.
Yes, that is the secondary terminal voltage for 0.8 lagging power factor. Okay, now calculate the voltage regulation E2 minus V2 by E2. This 52.96 divided by 500.
So 0.10592.
0.106.
0.1059 per unit. If you multiply it by 100, you will get percentage voltage regulation. So that is question number A. Okay. Now for question number B, 0.8 leading power factor. Okay. So here, what will be the modified formula for calculating this secondary terminal voltage?
Negative sign will be introduced, sir.
Yes, this sign, this plus sign here, this will be negative. Okay, the rest of the things remain same. So calculate using this formula.
Minus 13.16.
Minus 13.28. Okay, 16 is okay. Now calculate the terminal voltage V2. Obviously, it will be 513.28.
513.28.
Yes, and then voltage regulation.
Point 02656.
You have to mention the sign also.
So minus 0.02656.
Yes.
Per unit.
Yes, or minus 2.656%. So when the power factor is leading, you will have negative voltage regulation. So what is the physical significance of this? Tell me. Leading power factor means what type of load? Inductive or capacitive?
Capacitive.
No, capacitive. Capacitive load.
Capacitive.
Yes. So when there is some capacitive load is connected, in that case, you see the terminal voltage is 513.28, which is greater than the induced voltage, that is 500. Okay. So if you connect some capacitive load to the transformer, its terminal voltage across the load will increase from its no load value. Okay. And in that case, this voltage regulation will be negative.
Yes, so like when it is negative, the voltage will increase with the load, I guess. So that is
Yes.
undesirable.
No.
Okay.
Not like that. It will happen.
Okay, sir.
Okay. Actually, voltage regulation, higher value of voltage regulation is undesirable. It is for both type of load. Okay. So we always try to keep the voltage regulation within a certain limit. You see, normally our household appliances or any appliances work on a fixed voltage, right? So we don't want that this voltage which appears across the terminal will vary too much. That is why some tolerance band is given, plus minus 5% or something like that. Okay, so we don't want that voltage varies too much. So that is why this voltage regulation is always tried to keep within a permissible limit. Voltage regulation with higher voltage regulation for inductive load as well as capacitive load is not desirable. Okay, but if it is within limit, then it is okay, both positive as well as negative. Okay.
Okay, sir. Yes, sir.
Okay, that's all about voltage regulation. Now the next topic is losses and efficiency. So what are the different types of losses in a transformer? There are mainly two types of losses. Okay, one is core loss and the other is copper loss or ohmic loss, which is normally known as I square R loss. Okay, and this core loss has two components, as we have seen from the equivalent circuit diagram as well as the phasor diagram. We have two components of core loss. One is eddy current loss, another is hysteresis loss. Okay, so PC is the core loss of the transformer and it has two components. One is hysteresis loss PH and the other is eddy current loss PE. So PC equals to PH plus PE. So the hysteresis and eddy current losses in the core have been found to be given by the expressions this is an empirical formula. Okay, so here kh is some constant, f is frequency of reversal of the hysteresis loop, you know, hysteresis loop, and bm is the maximum flux density, and this exponent x is some constant which is known as Steinmetz constant. Okay, and eddy current loss is given by this expression Ke f square bm square. K is another constant of proportionality, f is frequency of reversal, and bm is maximum flux density. Okay, so therefore the total core loss can be expressed using this equation. Now let us define all these quantities. So first kh, what is this constant? This is a proportionality constant which depends upon the volume and quality of the core material and the units used. Okay, so since this loss is related to core, that means this loss occurs within the core. So this kh, the constant of proportionality, it depends on the material of the core as well as the volume of the core and the units used. Okay, Ke is another constant of proportionality which is related to this eddy current loss. So its value depends on volume and resistivity of the core material. See that is also again the material property. Here this kh, it depends on volume as well as quality of the core material. Okay, and here Ke, that depends on volume and the resistivity. So resistivity is the core I mean the material property of the core. Okay, so again this Ke also depends on the material as well as the volume. And then thickness of laminations. So what is this laminations? Normally this core of a transformer is not a solid core, it is made up of stack of laminations. That means thin sheet of this iron, special type of iron, normally silicon steel is used, which is a better material from the point of view of this magnetic property. So this thin sheet of silicon steel is stacked one over the other. In between there is some insulation. So this Ke, that also depends on this thickness of the laminations. Okay, and also the units used. Okay, so Kh is constant of proportionality for calculating the hysteresis loss, and K is constant of proportionality for calculating the eddy current loss. Okay, and Bm is the maximum value of flux density in the core for both these losses. F is frequency of the alternating flux, and X is some constant which is known as Steinmetz constant, and its value varies from 1.5 to 2.5 depending on upon the magnetic property of the core material. Again, this constant x, its value also depends on the material property of the core. Is it clear?
So
This is
that
factual.
hysteresis loss is experimental or it can be derived?
Experimental. You cannot prove this formula because this value of x that varies for different material. Both this formula are empirical formula. Okay.
This is a factual thing, right?
Yes. You have to test for different materials and then you have to find this equation by some curve fitting method. Okay.
Yes, sir.
Okay, sir.
So this is empirical formula, not experimentally proven formula. Okay. Or theoretically established formula. Okay, next is ohmic loss. This is very simple. So whenever this transformer is connected to some load, so there will be some current flowing through the secondary winding, and secondary winding has some resistance, so there will be some I square R loss, and when the transformer is not loaded there will be no ohmic loss or I square R loss in the secondary side. But in case of primary winding, when the transformer is at no load condition, then also there will be some current which is exciting current, though its value is very small, so there will be a very small amount of copper loss, okay, in the primary winding resistance. And when the transformer is loaded, so there will be ohmic loss for both load component of current as well as this exciting current. So that is the ohmic loss in a transformer. So there will be ohmic loss in both the windings of the transformer. Okay, so in addition to these two main losses, there are some small amount of losses which are very negligible, but still they are present. So one of these two losses are stray load loss and dielectric loss. Okay, so what is this stray load loss? What do you mean by stray? Anyone?
Something, sir, which has not a house or what? Stray dogs, like example.
Yes. Actually, stray means aimless.
Okay, yes, sir.
Okay, so aimless. So that means stray load loss means there will be in a transformer there will be some aimless flux whose path is not defined. We have defined two fluxes, one is mutual flux or the main flux, and two other fluxes, one is primary leakage flux and second is secondary leakage flux. Okay, so that means two fluxes are there, one is main flux, another is leakage flux. Okay, besides these two fluxes there are some other fluxes which has no fixed or defined path. They are aimless but they are present. Okay, so those fluxes will also create some losses, that is known as stray load loss. And dielectric loss, you know this dielectric loss occurs in the insulation part. Okay, insulation means through which current is not allowed to flow, that means bad conductors of electricity. Okay, but there will be some leakage current, okay, through this dielectric. So due to that there will be some flow of current normally known as leakage current, and due to this leakage current there will be some loss, that is known as dielectric loss. So these two losses are very small in quantity, so normally they are neglected. So the main two losses are core loss and ohmic loss. Okay, any question? Okay, no. So next is transformer efficiency. Okay, as we have seen, there are some losses. So whatever we are giving input to the primary side, we are not getting that amount of power from the secondary side, because there will be some losses in between in core as well as in transformer winding. Okay, so there is the question of efficiency. The transformer is a very efficient machine having efficiency more than 90%, 99%. Okay, why? Because this is a static machine, no rotating parts are there. That is why this machine is very efficient. Okay, so how to calculate this efficiency? The efficiency of a transformer or any other device is defined as the ratio of output power to input power. Okay, this is the normal definition for calculating transformer. Calculating efficiency, or here we are considering the efficiency of a transformer. So efficiency can be defined as output power by input power, which we can write. See, output power is V2I2 cos theta 2. V2I2, that is the product of secondary voltage and current, so that is secondary volt ampere, and if you multiply it by power factor, you will get the active power. So V2I2 cos theta 2 is the secondary output power, and input power is this output power plus losses, because the input has to supply both this output as well as the losses. Okay, so input power, without measuring the input power, we can calculate the input power using the output parameters and the losses. Okay, now see, using this equation, we can calculate efficiency without measuring the input voltage or input current or output voltage or output current. V2I2, that is the rated power given on nameplate of the transformer, that is the kVA rating or VA rating, that can be that we can get from the nameplate of the machine. Core loss, this can be measured by performing this open circuit test that we will discuss after this topic, and ohmic loss, that can be measured by performing short circuit test. Okay, so by measuring core loss and ohmic loss, we can calculate the efficiency of a transformer if the load power factor is given. Okay, because this kVA rating that we can get from the nameplate data, that is V2I2, and power factor it will be given, and then by measuring the losses only we can calculate efficiency. We don't have to measure the input voltage or current or output voltage or current. Okay.
Yes, sir.
So PC is total core loss here, which can be measured by performing open circuit test. I2 square Re2, that is the total ohmic loss. Why it is total ohmic loss? Because we are using the resistance, total resistance or the equivalent resistance of the transformer referred to secondary side. Okay, so that means it will give the total ohmic loss of the transformer which occurs in both the windings. Okay, and V2I2, that is the output volt ampere, which is given on the nameplate of the machine. And cos theta 2, that is equal to load power factor. This has to be given, load power factor has to be given, then we will be able to calculate efficiency using this formula. Okay, as stray load losses and dielectric losses are small, therefore they are neglected. Okay, as I have already mentioned. Now this efficiency can also be expressed using this formula, that is 1 minus losses by input power. Okay, output power can be expressed as the difference of input power and losses. So input power minus losses, that is actually output power. So if you divide this by input power, you will get 1 minus losses by input power. Okay, so losses we have measured, and input power we have calculated using the nameplate data and the losses calculated. Okay. Under normal operating conditions, the variation in the mutual flux phi is not more than 2 to 3%. What is the meaning of this? As we have mentioned, as I have mentioned, that mutual flux cannot vary. If the load current changes, then there will be a reflection of the same in the primary side. Okay, the primary current will change due to the change in the secondary load current. Okay, the exciting component of load primary current remains same. Since the exciting current remains same, therefore there is no variation of flux phi. Since the flux phi remains constant, now recall the expression of PH and PE. PH is KH F Bm to the power x, and P is KE F square Bm square. So Bm is phi m by A. So if phi m remains constant, that means Bm is constant, which means this core loss, since the flux does not vary more than 2 to 3% due to the variation of load, therefore this core loss component of core loss in a transformer is constant. That is the significance of this statement. Is it clear? There are two losses, PC and PCU. This is core loss and this is copper loss or ohmic loss. So when the load varies, that means when I2 varies, then there will be no change in this core loss part, but only this copper loss will change, because copper loss is expressed in terms of I2 square and Re2. So if I2 changes, this copper loss will only change. Okay, so that is the significance of this statement. So the transformer core loss is almost independent of load current. So with the variation of load current, there will be no change in the core loss. But the ohmic losses depend on the load current. So how to incorporate that load current variation in while calculating this efficiency? That means for different load current we will have different efficiency, because this copper loss will vary. Okay, so we need another equation for calculating efficiency at different loads. Okay, so let us consider some load which is n times the rated load. Okay, so current value will be n times the rated current. If I2 is the rated current, then for any load, say n, the current will be n I2. Okay, so in that case, the expression of efficiency modifies to this. So here we have to replace all I2 by n I2. The previous expression, in previous expression, we have to replace all I2s by this Ni2. Okay, so previously the formula was V2I2 cos theta 2. So I2 is replaced by Ni2, and then here V2I2 cos theta 2. So again I2 is replaced by Ni2, and PC remains same because it is independent of load current. Now copper loss, it was I2 square Re2. So I2 is replaced by Ni2. So now Ni2 whole square into Re2. Is it clear?
Yes, sir. Yes, sir. Clear.
So suppose n equal to half. That means we are running the transformer at half load. So you have to put half here. Then you have to calculate the efficiency. Suppose n equals to 1/4. Then we have to put n equals to 1/4 here. Suppose n equals to 1.25 times of rated current. Okay, so the transformer is overloaded, but still we can calculate the efficiency. Okay, so in this way you have to put the different values of n in this equation to get the efficiency at that load. Okay, again in this form we can also express this equation. 1 minus losses by input power. Now the condition for maximum efficiency,
Sir?
this is very important. Yes.
Sir, if load is n times, then current should be 1 by n times. Because
No.
voltage cannot be changed, right?
No. Here load means load current. When you are loading any device, that means you are increasing the load current, not the impedance. You are not increasing the load impedance. If you increase
sir.
the load impedance, then load will decrease. Okay, so loading a machine means you are increasing the load current. Okay, so n times means n times the load means n times the rated load. Okay, so some load is connected for which the transformer is drawing rated current I2 rated value. Okay, so this is the rated current. So when the machine is uh, underloaded, suppose half loaded, in that case this I2 will be half times I2. That is the concept. Okay.
Yes, sir.
So condition for maximum efficiency. So this is the formula to calculate efficiency at rated current. So the efficiency will be maximum when the load current, if we take the derivative of this expression with respect to load current, that means for a given current, for a particular current, the efficiency will be maximum at a given load power factor. We here V2, the load terminal voltage, power factor, and all the losses, that means not all the losses, the core loss are constant. So we have to find the value of current at which the efficiency will be maximum. Okay, so since we are varying the current to get the maximum efficiency, that means maximum efficiency does not occur at rated current. Okay, so I2 is rated current, so at that current maximum efficiency will not occur. It will occur at some other current value, at some other load value. So we have to find that current and the condition for which this efficiency will be maximum. Okay, so let us see. So taking derivative of this expression and equating it to 0, we will get the condition for maximum efficiency. So if we differentiate this, we will get the condition as I2 square RE2 equal to PC. So you differentiate this and find either you are getting this expression or not. So that is the condition. Here I have skipped this derivative part. Okay, you know better how to differentiate.
Yes, sir.
So the condition for maximum efficiency is that when the load current is such that it will give the copper loss value exactly equals to the core loss value, then the efficiency will be maximum. Okay, that means this this fixed losses will be equal to variable loss, then we will get maximum efficiency. Okay, PC is the core loss, which is constant loss, and I2 square RE2, that is the variable loss. So the current value for which this variable loss becomes equal to the fixed loss or constant loss, that is core loss, then we will have the maximum efficiency. Okay, so this is the condition for maximum efficiency. So what is the value of this I2? That you can calculate using this expression, that is I2 equals to root under PC by RE2. So the condition is variable ohmic loss is equal to constant core loss. The load current at which the maximum efficiency occurs is given by I2 is equals to root under PC by RE2. So that is the load current value. So at this current, efficiency will be maximum, which is given by this expression, that is root over PC by RE2. Okay.
Sir, why did we tell that the current is variable? Sorry, the loss is variable. The core loss.
Core loss is fixed.
Sir,
Not
in the
variable.
last PPT, previous PPT, previous slide.
See,
Variable ohmic loss.
loss is equal to constant core loss.
So why we are using variable ohmic loss? So our power factor and everything is fixed. So and I2 we are calculating. So why are we telling it to be variable?
No, this ohmic loss is variable because it depends on load current. If you change the load current, ohmic loss will vary. PCU, this is copper loss or ohmic loss, which is given by I2 square RE2. So this I2, current I2 is variable. It depends on load. So if I2 varies, then PCU will vary. But core loss, PC, that is constant because the flux is constant. Got my point?
Yes, sir.
So this load current value is equal to root over PC by RE2. Now that can also be calculated using this expression, that is PC by IFL square RE2. What is this IFL? That is the rated current. IFL means I full load, which is rated, or I2R. We have used this symbol also while calculating this voltage regulation. So IFL, I2R, they are same. So at full load, if you calculate the copper loss and take the ratio, this ratio PC by full load copper loss, and taking the square root of that, and if you multiply it by this full load current, then you will also get the load current value for which this efficiency will be maximum. Okay, so in either way you can calculate the load current value for which max efficiency will be maximum. Either use this core loss and equivalent resistance referred to secondary side, or you can calculate the full load copper loss and then applying this formula you can calculate the maximum current value for which maximum efficiency will be maximum. Okay, now see this RE2, you have to determine this RE2 by performing open circuit test, short circuit test, and this IFL square RE2, that is the copper loss, this you can determine by performing only short circuit test. By running the transformer at full load current and performing the short circuit test, you can measure. So this is a measurable quantity, and PC you can perform open circuit test to measure core loss. So both are measurable quantity, but RE2 you have to perform these two tests, then you have to calculate to get RE2. Okay, so that is why the second formula is better. You can directly calculate the I2 value using these parameters PC and copper loss at rated current or full load current, and full load current, that is also a measurable quantity. From ammeter reading you will get full load current. Okay.
Yes, sir.
Now another way of expressing this formula is that if we multiply both sides by secondary rated voltage and dividing the expression by 1000, then we will get the kVA rating. See E2 I2, this is the kVA load at which this maximum efficiency occurs. E2 IFL, this is the kVA rating, because E2 is rated secondary voltage, IFL is the rated secondary current. So product of these two divided by 1000 will give you the rated kVA. Okay, so this is the kVA at maximum efficiency and this is the kVA at rated condition, and this remains same, ratio of copper loss to ohmic loss at full load current. Okay, so we can express this equation as like this: kVA load for maximum efficiency is equal to rated kVA into root over PC by PCU at rated current. Is it clear? From this equation you will be able to calculate the load current. From this equation you will be able to calculate the load kVA, kilovolt ampere loading. Okay.
Yes, sir.
So mathematically we can write like this: kVA at maximum efficiency, this is rated kVA, and this is PC by full load copper loss. Okay, so that's all about losses and efficiency. Next is open circuit test and short circuit test, but time is almost over. Okay, let us end here. We'll discuss this topic in next class. So can we have a class tomorrow? What have you discussed about that?
No, sir.
So decide it and confirm me by today's evening only.